Hello, my name is John Haddad. I am a Cassandra committer, and I gave a talk last month at the Cassandra Summit back in December. Um, I didn't know that I would only have 25 minutes, so I was trying to cram a lot of material into a very small window of time. And unfortunately, I also had a technical glitch with my slides. My slides um, weren't really you couldn't read them. The resolution on the monitor was all messed up. So while the talk is online and there's a lot of I think good material in there, I think we can do better. So this is take two, and it's going to be a slightly extended version. I have as much time as I need. So I'm going to spend about 40 minutes talking, going through my slides in the talk, and I'm reserving about 20 minutes for Q&A. I don't know if they're going to wind up being exactly that, but I'm going to be here till 11. So you got me for an hour if you're here. Um, oh, hey, how's it going, buddy? Yeah, so I'm just gonna jump into this, and I'm gonna get started. Um, so my talk is Cassandra Performance Tuning, like you've been doing it for 10 years, and this isn't. Um, is my mic on? Yes. Okay. Good. Uh, this isn't. This isn't made up. I started working with Cassandra back in the 1.1 days. I was on the first team that I know of to put CQL in production. Um, I've got definitely a good amount of experience with this. Um, I'm one of those people that actually enjoys fighting the dumpster fire. I've been in a lot of different situations that have required me to kind of figure out what's going on when there's a lot of broken stuff. And I definitely ended up focusing on performance side of things because in a lot of cases I was limited by budget, and so I didn't really have the privilege of having these enormous budgets where we could just throw money at the problem. That was like a crazy idea. Working at small startups, so I got really into the performance side of things. Um, After my stint at startups, I moved on to DataStax, where I worked with Patrick McFadden, who's well known in the Cassandra community, um, speaking all around the world, helping people get started with Cassandra, use it effectively. And then I moved on to the last pickle, and that's where I spent a lot of time focusing on performance stuff. Pretty much any performance question that came into TLP, especially if it was in the U.S. and the time zones lined up, like it was basically me trying to solve these problems. So while I was there, I worked with over 100 teams on solving a wide variety of problems, but um, a lot of them were performance problems. And then from there, I that's when I was added as a committer and to the PMC. Then I joined Apple, worked on the 4.0 release. I built a lot of the tooling that we used for testing. From there, Netflix, where I worked on the again database team. I ended up doing a lot of the performance optimizations and for various clusters around Netflix, GC tuning for the entire fleet, optimization of things like the subscriber database and the database that essentially houses all the raw data that powers all the machine learning that changes your experience. It's what customizes your experience for you. So I worked on all these systems, and they're really interesting. I definitely noticed a lot of patterns, and between my time at TLP, Apple, and Netflix, I can say that I've seen a lot of stuff. So I left Netflix in March, and so since then I've been running my own consulting company. So it's been 10 months, and uh, things are going great, and they're fun. And I get to help people solve interesting problems. So I'm really excited to share some of the stuff I've learned with you. One of the interesting things I think that we have to answer is why do we even care about performance? Performance is one of those weird things, especially when it comes to performance tuning, where folks don't quite realize the impact that having a well-tuned system can have. So if we think about the three main reasons that we're going to care about, the obvious one is user experience, right? If something is taking multiple seconds to load, if it's a mobile app or even desktop app, like any time that people are sitting around waiting, it's been documented many times that this is one of the worst things that can happen for your end user. People will just leave. They're not interested in using applications that are slow. Um, we also have its impact on availability. If you have a well-tuned system, let's say you have, an individual server and it's well-tuned and you're running your CPU at 50% versus something that's not well-tuned and you're running your system at 99% um, capacity, then you have a lot less room. So if all of a sudden you get a usage spike, you can end up seeing your untuned server is going to start experiencing problems way before your tuned server. And the last one is cost. With something like Cassandra, you'll sometimes hear people talk about it being storage bound, which isn't really, in my opinion, it's not really a great term to use. I would, I'd almost consider it it's kind of a wrong term to use because there is no such thing as storage bound. We can always add more storage. Um, but Cassandra can be CPU bound and it can be IO bound, and there's two different kind of reasons why it would be like that. But either way, uh, if we need to add more hardware because we're not using our current hardware efficiently, that's obviously going to be more expensive. And in my experience, we're not talking about 2, 3, 4 percentile, like percentage points difference. I've worked in systems where I was able to uh, get 10x improvement in throughput and latency. And so, when we start talking about that, like if you can run 3 servers instead of 30, that's like $150,000 difference a year if you're running an AWS. Like it is a huge, huge difference. And being able to run denser nodes is the key to keeping your costs low. So the better we can optimize performance in Cassandra, or any database for that matter, the cheaper it is to run. And that's one of the main things that I like people to understand is that this is, like I said, it's not just 3 or 4 percentage points. It's real money. It's 2, 5, 10x difference. So if you can cut your costs by 90%, uh, you're going to be in a really great position. Especially, small startups, really useful. Like there's not a lot of spare cash usually at small startups. And the idea that we're just going to throw money at the problem doesn't always work that well. Even at large companies, if you were to take uh, Netflix's Cassandra fleet and successfully cut it in half, that is a significant savings. Or any large Cassandra user, CrowdStrike, Spotify was an old one. Um, these are essential. You know, it's essential to be able to kind of consider your costs and to get it done early is nice because you actually save money in the long run. So I want to talk before we get going about expert mindset. So the expert mindset is something that we need to adopt that allows us to solve problems in a methodical manner. So we're going to start. There's three components here that I want to touch on. One is the methodology that we're going to use. So whenever we need to solve any problem really, or I mean performance problems, yes, but any problem at all, whether it be something is downtime, whether it be availability issues, or just jittery servers, or we want to fix GC pauses, whatever it is, we need a methodology. Okay, so first we're going to look into that. Second thing that we're going to look at is observability. So this is a core pillar of doing any sort of performance tuning, and I'm going to talk a little bit about more about that in a minute. And the third one is practice, and this is one of those things that may not seem obvious, but it is really really important that we try these things out in safe environments in order to become good at them. Just like you couldn't if you couldn't pick up a book and about guitar and read it and then go on stage and be expected to perform. You need to practice. You need to learn chords. You need to learn melody. You need to learn music fundamentals. Maybe not music fundamentals. Some people can just play, but you really need to practice. Okay, so getting started with methodology, right? A lot of the time, a lot of what I've seen over the years is someone hits a performance problem and then people just start changing configuration or guessing at what it might be. The time for guessing is in practice. The time for experimentation is when we have no consequences, where we can safely make changes and not affect a production environment. Once you've done this a bunch of times, you can definitely get a feel for the things that you should change or you need to change. And I'm generally pretty confident about the changes that, especially some of the ones that I'm going to be talking about today, the changes that I'm going to be suggesting, we can make them without a high risk. But there are some changes that if you don't understand what the trade-offs are, you can find yourself in a bit of a difficult situation. So the first thing I want to kind of bring to the table is something called the OODA loop. The OODA loop is incredibly useful for problem solving. And it stands for observe, orient, decide, and act. Okay, this was developed at the Air Force. And what it means is it basically breaks up the problem solving process into discrete steps. And the reason why this is nice is because it prevents you from, when you do the steps in order, it prevents you from making unsound decisions, or it also prevents you from guessing. So the first step is observe. So we want to be able to have a good set of tooling, and generally this comes in the form of dashboards and tools in Linux. We need to be able to make observations about our system. I have worked in way too many environments where people make an assumption about what's happening in the underlying hardware, and then they make decisions based on that unvalidated assumption, which has actually led to weeks of lost time. So you really want to make sure that you understand, like, if you come up with an idea or a question, you need to be able to validate your hypothesis. So the first stage is observe, right? That's where we're collecting information, we're running our tools, we're figuring out what's going on. And then orient. Orient means that we're going to take all the information that we picked up in the observe phase, and we're going to build a mental model. So if we see high I/O and high CPU usage, that tells us something, right? So we need to then take a course of action that takes these things into account. We need to figure out, okay, why is this happening? Well, if we have high CPU usage, what could it be? Could we also be having, like, in Cassandra, could it be a lot of compaction? Could it be a lot of requests? Or could there be something else that's going on? What if we have a lot of I/O and really low CPU usage, or really high CPU usage and low I/O? There's different things that can be wrong depending on what you see in this type of setup. And so it's really important that we orient ourselves the correct way. And then finally, once we have our mental model, then we can make a decision. We can decide what we're going to do and who's going to do it. And that's the decide and act portion. So the decision on what you're going to do is going to be, it should be an informed decision that you get from that orient phase. And now the next thing that I'm going to talk about is the use method. And so there's really two approaches to kind of looking at a piece of software and understanding where its bottlenecks are. With a database, the use method is typically going to be the thing that you're going to want to rely on. You can also do thread analysis, but the use method is fantastic. And what the use method stands for is utilization, saturation, and errors. And what you want to do is you want to take a look at all your resources and understand what your metrics are for those three things. So for utilization, We're just talking about the average time that the resource was busy servicing work. Okay, easy kind of no-brainer example is your CPU is at 90% utilization. That means that your CPU is busy 90% of the time. It's doing something. It could be waiting on I/O. It could be waiting on main memory. But it's busy. It's doing who knows what, right? One of our jobs is to figure out what the CPU is actually doing. We'll get to that in just a moment. So then we move on to the S, saturation. So this is the degree to which the resource has extra work which it can't service, often queued. This is very easy to look at if we take a look at our I/O device with IOStat. IOStat is a Linux tool in the systat package. You'll see that there's an average queue size. That's a metric that you can get. I think you need to use the -x flag for extended, and then you'll see. I usually, when using IOStat, I usually use the flags -dmx. That gives me all my devices, puts the numbers in megabits, or sorry, megabits, and the X is for extended. So you get a ton of information, but you actually really get a lot about what your system is doing. So one of those things is going to be the queue size. And then the last thing is errors. And errors are really important. A lot of people forget about errors. The reason why errors are so important, it doesn't matter if you serve your requests in sub-millisecond, if 90% of them are failures, if they error out. That does the user no good. So you have to make sure that you understand how to figure out what your error rate is for all of your things. So dmessage is really useful for this type of thing. You'll actually see error messages show up in dmessage if you have like a corrupt file system, or your device isn't there's an issue with your device, or you're using an old version of Linux kernel and you're trying to use NVMe devices. Old versions of Red Hat actually shipped with a horrific bug where NVMe devices just didn't work. And so you can rely on dmessage to see the what's going on here. Another good example of this is TCP retransmit. If you're losing packets on your network, TCP retransmit is going to show up, and that will show up in your TCP statistics. So now that we have this kind of thing that we can rely on, the use method where we say, okay, we're going to collect information, and now we have the use method which tells us how we're going to collect the information. Now let's move on to a little bit more observability. So using dashboards is the number one thing, right? We need to be able to aggregate all of our information and have good dashboards. And I've got some grievances about the way that most folks do dashboards. I'm going to talk about those in just a moment. This screenshot is actually from the AxonOps tooling. I've worked with them a little bit recently, and I really, really like what they're up to. They have this nice view of aggregated logging and metrics in the same view. It actually is really helpful when you're trying to diagnose problems. And I thought this was pretty interesting because most tools kind of keep that stuff separate, but they integrated it in a really clean way. So dashboards are the number one thing. And with dashboards, you want to make sure that you're able to spot outliers. You want to make sure that you're able to answer the question, what is the worst performing node, or which table gets the most queries. If you can't answer those questions, then your dashboards are not giving you the answers that you need. They're probably more like something really pretty that you can look at. I've worked with a lot of teams, and I've worked with a lot of different tooling, and honestly, I think almost everybody gets it wrong. And I'll tell you a few reasons why about that. So one of the things that I've seen wrong in dashboards almost everywhere is using metrics that don't make sense. So using averages, for example, is a terrible way to convey how your database is doing from the perspective of what's the end user experience. You could have half your requests be really slow and half be really fast, or you could have it be in this weird curve. So what you want is to actually graph the P99 and your maximum for anything where there's a latency. So you don't want to spend time looking at P75, P50. I've seen teams graph P75. This is a massive issue for me. There's actually a link in the description for a video from Gil Tene, the CTO of Azul, and he has an entire hour dedicated to talking about how our understanding of metrics is usually wrong and how almost everybody does it wrong. And it's really interesting. I highly recommend watching this video. It's an hour, but there's a lot of really good stuff in here. And what he goes to show you is that you can miss a lot of really critical information if you're not willing to graph the extreme end of the tail. If you focus on P75, even P90 or P95, you'll miss out on a lot of useful information because, especially with a database like Cassandra, which is based on the JVM, if you're getting 500 millisecond pauses or 800 millisecond pauses or something, a whole bunch of your users are going to get a really bad experience, but it's going to affect such a small percentile of them that you might not notice it. So that's hopefully you can watch that, you can get a better idea for what's going on, but hopefully if you don't, hopefully that was enough. And like I said, you don't want to hide outliers. That's why I said you want to graph the max. So P99 and max is super important. You don't want to throw away the max. Another big mistake that people do is they average summary data. So what you might see, for example, is someone take P99 from each node in the cluster and then average those numbers together. And that doesn't actually tell us anything either. Like, that is a completely useless number because one node could have 1 million requests, another node could have 10 requests. Averaging those together doesn't mean anything. It's 1 million and 10 requests at whatever. So unless you're like taking all the requests and making sure that you account for like the total count and using like proper statistics, it doesn't help. And that number isn't really that useful anyway. So my recommendation is to stop averaging this type of data and only plot the top 3 and like the bottom 3. And if you're going to plot the middle still, you can plot it as a line through the middle. But there's no reason why you need to see the middle band of performance. So it's a really good idea to just say, what's the worst 3 nodes or the worst 5 nodes, whatever, some number that you have. If it's a 300 node cluster, you can't really do much with a graph that has 300 lines on it. You only really want to see the worst ones, because the worst ones, when it comes time to look at a performance problem, you want to look at the worst performing nodes first. And then the last one, I put this as an anti-pattern, but this is just I guess it's just a general problem. Not understanding your tool's output. So a really good example for this is when people use IOStat. IOStat has a flaw in it where when you look at one of the last columns, it'll say %util, that's percent utilization. That number isn't actually useful at all with anything other than spinning disks. Like if you have an SSD which can perform multiple requests in parallel, %util doesn't tell you anything useful. So if you see it's at 100%, it might not be at 100%. In fact, it's probably not at 100%. So don't rely on %util for anything, and make sure that you understand what your tool's output means, right? Sometimes this means just getting familiar with the terminology. Don't guess, read the man page. Like the man page for IOStat says, don't use this column. It's silly. So definitely make sure you know how to interpret the results from the tools that you're using. And speaking of tools, there's a lot of them. I got this from Brendan Gregg's Linux Perf page. Brendan Gregg is ex-Netflix. He worked there for maybe 10 or 11 years or something. One of the top performance experts in the world. So this is a really good page, and it shows you for the entire kind of like stack of stuff, like what you would want to use to understand it. And there's even more tools than this. This is actually just a sample of tools really. So I highly recommend kind of getting familiar with some of these tools, and I'm going to do some follow-up videos where I talk about this, each of these tools or some of these tools in detail. Right. At a high level, at least there's one package that you have to get familiar with, and that is Systat. I already mentioned it already. IOStat is one of the tools that's in Systat. So is MPStat. MPStat is an incredibly useful tool. Again, this is a high-level tool. Once you're SSH'd onto a box and you're trying to figure out what's going on, a lot of the times dashboards don't update fast enough, or the metrics aren't collected fast enough. You want to be able to get faster information. So that's why I always SSH into boxes. MPStat is really nice because you can use this -p flag for processors and then all, and then your interval and your count. And it will sit there and it will show you per processor how much CPU time is being taken, how much of that is being spent in I/O. And you can see here 75% of my time is being spent in I/O in this example. So I think I was running the FIO tool, which is a disk benchmarking tool. It's used to benchmark the Linux kernel. Really, really helpful. But this is nice because it gives me an idea of what to look at. And this isn't one of those things where you just look at it and immediately come to a conclusion. We're not just going to assume that we have a problem with compaction because we have high I/O. Like, it's not reasonable to assume that. It could be something else. So when we want to start digging in, I really have found eBPF and more specifically BCC tools to be useful in diagnosing some very, very, very tricky problems. I'll talk about them in just a moment. So one of the questions that we can kind of postulate, right? We can say, what happens if we give Cassandra a bigger heap, right? This is not unreasonable. If you're running Cassandra with 8 gigs of RAM and you're sitting there and you're going, well, I'm having long GC pauses, maybe I should give it more heap. But you don't have that much memory on the box. So what trade-off do we make when we do this? So it's kind of an interesting question because there's a handful of things that can happen, right? We take away, when we give memory to one resource, we take it away from another resource. In the case of memory, the thing that we're taking it away from is typically going to be page cache. Okay, so when we give more memory to Cassandra in the hopes that we're going to just fix GC pauses, which it doesn't quite work like that, but it's one of the steps that we would do to try and alleviate GC pauses. Then we're going to say, well, if we take memory away from the page cache, then maybe we're going to see a worse cache hit rate, right? And when we get a worse cache hit rate, that means we're going to see more I/O. So if we're going to give Cassandra more heap, we definitely want to understand if we've negatively impacted our page cache hit rate. That's where this CacheStat utility is from. CacheStat is part of BCC tools, and under Ubuntu and Red Hat, they have different packages that you can install, and in AWS it doesn't quite always work correctly. I've had some issues with the installation not working right, so I've had to build it myself. But CacheStat is really nice for understanding what your statistics around your page cache. So instead of just saying, well, I assume that if we give more memory to the JVM, then we're going to have a worse cache hit rate, we can actually test it. We can look at the before and after. So this hit ratio is the easiest thing that you can look at. You just run CacheStat for a little while, take a sample, and figure out over time what your cache hit rate is. And then when you change your JVM settings after it's been running for a little while, you run CacheStat again, and you look at your GC pauses, and maybe you conclude that this was a helpful change, and you look at your cache hit ratio and your I/O usage, and you figure out what's happening there. And then you also look at your latency on your requests, and you figure out, okay, what was the impact on my latency? This is a pretty kind of straightforward thing to do if you know the right tools to use. But if you don't know the right tools to use, and I've encountered very few people that do, this can actually be kind of a giant question mark because it's like we're making changes and it's like the person with the blindfold at the beginning turning the knobs. We don't know what we're doing. So we definitely need to make sure that we have the right tools to monitor things like cache hit rate. And then we might ask ourselves, well, what's actually happening at the file system level? So BCC Tools, again, comes with an incredibly useful tool. I'm running this on an ext4 file system, but the same thing exists for BTRFS, ZFS, XFS, you name it. All the file system operations, all the statistics that this gets the operations from are actually against the virtual file system, which is an abstraction that all the file systems sit under or sit behind. So we're just getting statistics from the file system. And so this will actually break out. If you look here, we can see how many, we can see the distribution of request times for the different operations that we do. So we know how long these reads and writes take. And the -m flag just means do it in milliseconds. So this will show us now every second, 20 times, it'll show us the distribution of response times from your file system. And this is typically going to be in a bimodal distribution. We're going to see like a big fat number for requests that end up hitting page cache, and then we're going to see some that go to the underlying block device. We then might ask ourselves, well, what's the block device doing? This is a really useful question to be able to answer in a situation like if you're using EBS. So I've worked, or SAN. I worked on these two problems in the last 2 years. A team was using a SAN, another team was using EBS, but it's the same underlying problem. And they were having performance problems. And they said, John, like, we have EBS here, we're gonna blame EBS for the problem. And EBS has gotten a lot of flack over the years because initially when it got rolled out, it was not that great. But in the last, I'd say 5 years, maybe a little more, it has proven to be pretty damn reliable. Like, it generally just works. Occasionally you'll see a blip. It can be a little hard to understand the underlying metrics and to know to zoom in. You have to, if you want to tell if you've hit the IOPS limit, you have to actually zoom in. It won't be obvious. They don't show, they don't highlight your spikes. They don't use a very good graphic algorithm, and they don't visualize it well. So you need to zoom in real close to determine if you hit your IO limit. But another way to do it without relying on their graphs, you can use a tool like biolatency. So biolatency does something very, very similar to the EXTFS and XFS type tools, but this will actually show you the count and distribution of requests to a block device. So this doesn't include any of the page cache stuff. So for example, to go back to my earlier example of EBS, we were seeing a very, very high P99 response time, and P98 was very low. And this is why I say that you need to graph everything, because this is a really perfect example. The team was blaming EBS, and this was I think this was like a 600 node cluster. So changing this around, it was one of the most important clusters at this company. It was a big deal. So we weren't, we wanted to take this kind of carefully. And so, everybody was blaming EBS, but once we took a look at biolatency, it became really obvious that EBS wasn't actually the problem. In fact, when we look at the other statistics, we could see that that the underlying file system, the underlying block device, all the metrics coming out of Cassandra for the storage was all fine. In this case, it turned out that someone had accidentally enabled read repair chance, and this was a multi-DC cluster. So read repair chance 1% of the time was going out and doing read repair, and then the metrics for Cassandra are reporting the included read repair time. And it's also a blocking operation. So we were actually in some cases seeing timeouts. So in the case of a read repair taking longer than the very low timeout threshold that they have, they would get an error message back, and it would say, can't read timeout, can't satisfy at consistency level all. So they're off looking for, all, blaming EBS, but really it's just this one setting which is wrong. So flame graphs on tooling. Flame graphs are, without a doubt, one of the most useful tools I've ever come across. I think it's really important to understand how to get a really good profile of your hardware, and that's where BCC tools and eBBF come in. In fact, I have links in the description. I've written a couple blog posts recently on both BCC tools and BPF Trace, which is a tool I'm not covering today, and flame graphs. So that's all further reading if you're interested in getting to know more about this topic. But what flame graphs are a visualization of profile data. So let's take a look at this one, for example. I have a little arrow drawn there, and there's a nice big line with some red on it. And that is where a lot of the time is being spent in this workload. And I don't know if it's easily visible, but basically what it says is that it starts with LZ4. Okay, so even if we don't know anything about Cassandra, even if we're clueless, we can take a look and we can say, well, LZ4, I know what that is. That's from compression, right? Compression sitting there. Well, how does compression work? Like, why would something related for compression be taking up a lot of time? Like, maybe we should figure out how that functions. Well, compression is, if you haven't seen it, as part of your table definition, and you may not have ever supplied this before. If you take a look at your table definition, though, you will see it. And it will say with blah, 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 compaction, read repair chance, Bloom filter, false positive, compression. Then to say SS table compression, we're going to use LZ4 compressor, and it's going to say chunk length in KB, and there's going to be a number there. Now that number is going to depend on which version of Cassandra your table was created on. If you're creating tables pre-4, I think it was pre-4.0 or pre-4.1, this chunk length in KB is going to be 64. Okay, if it's after, it's going to be 16. Now, the reason why this is interesting, first of all, this is how compression works. Whenever we're going to write data to a disk in the form of an SS table, first we have a buffer. Okay, that buffer gets filled with data from that's going into the SS table, and that buffer is the size of that compression chunk length. So this is a chunk. So by default, if we're doing 64 KB, that means we have a 64 KB chunk, right? We write our data, we compress it, we write it to the SS table, and we put additional metadata about the compression information, what was there. When we want to read this information, it's the opposite. We read the metadata, we figure out where we're going to go, we read the compressed block, and we decompress it. Now that's going to be 64K or 16 depending on the version. And this is interesting, right? But like, why does it matter? Well, if you take a look at node tool table histograms and you go down to your partition size, or you're doing small reads, you can just be doing individual row reads, but partition size is a really good thing to look at because it covers the maximum that you could possibly read. So if you look here, this table is really tiny. It's probably just like an integer or something. But you look and you see the partition size is 35 bytes. And then we go out to P99 and it's 35 bytes. And our maximum is 35 bytes. So this is a really small table. In fact, I think it says I have one cell here. If you have a table where you consistently have small partitions, and this is consistent with database schemas where maybe it's a user login type table or just a user metadata type table, any non-time series key value kind of table where you're not dealing with a clustering column and lots of rows inside a partition is generally falls into this category. So the problem is that when you read all this data, when you read 64K, you read, depending on what your compression efficiency is, maybe it's 50%. So now you read 32K off disk, you decompress it, now you have 64K. Some of that does JVM allocation, you got a bunch of objects that we're gonna look through. And then we return these 35 bytes, okay? This is read amplification. This is terrible. This is not what we want, because we only needed to return 35 bytes and we just read 32, let's just call it 35K just for the sake to make the math easy. That's 1,000 times the amount of data that we needed to read off disk. That's crazy. We don't want to do that. We've also done a ton of allocations in the JVM. So now we're actually putting a lot of pressure on the JVM. We don't want to do that. We want to keep things as tight as possible. We're going to do the minimum amount of allocation. We're going to do the minimum amount of I/O. Because when we do read amplification, if we start to hit a read spike, we're actually going to hit the maximum utilization for a drive. Like a drive, like any other resource in your computer, remember, it has its limits. So if you hit your throughput limit because you're doing read amplification, it means that you're going to see a very, very tiny amount of network usage. You might see low CPU usage, but you might see really high I/O, and it's no good. You might actually also, you're probably going to see high CPU usage because it's going to be time is going to be spent in I/O wait. So, it's definitely a good thing to take a look at. You do not want to see read amplification, and I don't know if this is, I'm not sure if anybody else uses this term, but you're also seeing JVM allocation amplification, and these things are no good. So you want to make sure that you size your compression chunk length to a size that is most appropriate for your data. So if your data is sitting and you've got, measuring it in hundreds of bytes, you can get a huge benefit from going from 64K to 4K. It will make your compression efficiency a little worse. It does allocate more memory on the heap to keep track of the compression metadata, but you do less I/O. So this is one of those trade-offs. This is where we say, okay, like, do we have the memory to be able to handle this? We might actually need to increase the size of the memory, the heap that we're giving Cassandra in order to keep all of the compression metadata. But that's generally okay, and that's why we want to have the right tools to be able to understand, do we make the right change? So to do this change, it's actually pretty simple. Just alter the table. You throw in some new compression metadata and new compression chunk length. This will cause new SS tables to use the new chunk length. The old ones will use the old chunk length until they're either recompacted or you force them to be rewritten using node tool update SS tables. So believe it or not, this is one of the most impactful changes that you can make on a system. So remember, I said that before reducing I/O by 16x, there's a reason why we've updated Cassandra to use 16 now instead of 64. It's because it actually gives a better all-around setting. If you know what you're doing, you should, and you know you're going to be doing big reads, you can go ahead and set it to 64. That's okay. If you know you're going to be doing really tiny reads, you want to bring it down. If you're using EBS, you want to make sure that you don't set it too small, because EBS actually measures your IOPS in 16 KB chunks. So setting it below 16 doesn't really do you any good on the IO side of things, because they're going to record their IOPS the way that they record it. You're kind of, you're in trouble there. So you want to either go to 16K, 32, if you're getting really great compression ratio. I remember, the lower the number, the better the compression ratio. If you're getting a really, really good compression ratio, then you can go 32 or 64. And you'll be okay. But the reason why this matters a lot is because it doesn't just affect workloads where we're reading tiny rows. It also affects workloads that do read before write. So 2 examples of this in are lightweight transactions and counters. So a lightweight transaction doesn't just do 4 round trips, pre-Cassandra 4.1 if you enable the Paxos v2, but Cassandra will do 4 round trips, and it also has to read the original data off disk. So that can be really expensive. If you're updating only 1 row, and you have to read a ton of data off disk, you can easily saturate your disks just from having a too high compression chunk length. It's actually remarkably easy. This is the easiest optimization that you can do. You'll see if you do this correctly, you know, on a reasonable system, you can get like a 2x improvement in your throughput and your latency just from this change. And the same goes with counters. Counters have to read the original counter. They have to read the current counter value and then apply the counter change and write all of it to the commit log. So if you're not tuning, like if you leave your counters table at 64K, you're doing a lot of I/O that you don't need to do, and you're actually going to hit JVM. You're going to hit long JVM pauses, and from all the extra allocation objects that are allocated, that's the JVM allocation amplification that I was talking about, and you're going to do too much I/O. So you're going to think, wow, Cassandra sucks at counters, but the real reason is just you didn't apply this one change. So definitely, if you're using these two things, be smart. Use lightweight transaction. Use small chunk lengths with lightweight transaction and counters. You'll be much better off. And you can see here, you know, this was changed. Okay, so it was 4.0. So I was involved in this change. This was I was really happy to see this change in. It's one of the reasons why Cassandra out of the box 4.0 will benchmark better than previous versions, because it just is smarter about I/O usage. So while we're talking about read amplification, there's one more thing, and this is something that I have been telling people. I've been telling everyone that will listen to me. If you're watching this and you're thinking to yourself, should I worry about this? The answer is absolutely yes. It's probably if you've never looked at this before, it's probably a major problem for you if you're dealing with anything that has if you're requiring low latency on small reads. So read ahead is this archaic setting that was used to help mitigate the slow latency associated with spinning disks. So what it would do, or the way read ahead works, is when you issue, or when your application issues a read to your operating system or to your disk, what happens is first read ahead steps in. It's like, whoa, me first. It reads the data off disk. Now it reads a fairly large amount of data, places it in the page cache, and then you actually get your response out of the page cache. And you can tell what the setting is by using, there's a couple ways to do it. The easiest way here is just to use block dev -- report. You have to reroute to do this. And what you'll see here are a few columns. The one that we're most concerned about right now is this RA column. So this 256, this means that we're reading 256 512 byte sectors. So you can just cut that number in half and you'll get the number of kilobytes that you're reading for read ahead. So every operation that you do, every I/O operation that you do that goes to disk, you're actually going to read 128K. Terrible, right? So if you go ahead and you change this using block dev -- set RA and you point it to the correct device, it will change it. It won't persist it across restart. I'm not going to get into that right now. There's multiple different ways that you can have that persist across restart, and I don't have a strong opinion on which one you use. But if you do that, then you will reduce the amount of read amplification as a result of read ahead. So when you take care of compression and you take care of read ahead, you actually can reduce for small reads. Again, this is super important with lightweight transactions. You can cut down your read amplification by a factor of like 10x, and that right there is something that allows you to get 10x throughput improvement through lightweight transactions. Easiest thing in the world. 2 settings, hardly any work. So the last thing I'm going to talk about here is practice. Practice is super important. The reason why I know this stuff is because I practiced. So I built multiple tools especially while I was at the Last Pickle. Last Pickle was just nonstop. I got to fix things that were crazy and figure out why all the underlying issues, why things happened the way that they did. So all I did was read source code and build test tooling and figure stuff out. And I'm also the most impatient person. So when I want a cluster, I want it right now. I want it in the next like 2 minutes. And there really wasn't a good option to do that. So I built TLP cluster. Last Pickle was acquired by DataStax several years ago, so now they own the tool. I'm not. They haven't really done a lot to update it over the last few years, unfortunately. I forked it, so it's in my repo. I'll actually update my the description with a link to TLP cluster if anyone's interested in it. My fork is completely broken right now. It's based on an earlier version, and I'm ripping it apart and making it a whole. I'm redoing it, but I like a lot of the stuff that's in there, and it's really good. And another option, if you want to just easily spin up a lab, AxonOps has announced at the summit. AxonOps announced that they've built a provisioning tool, so you can actually have AxonOps provision a tool in your own data center in AWS. And it's really cool because they have all the administrative tools that go along with it. They have a free tier, so you literally have nothing to lose unless you want to kind of roll your own, which is the route that I've always gone. But if you're just looking to test stuff out, like it's pretty easy to get going with either one. And then benchmarking. This is another area where my impatience was the thing that drove me to build a tool. So I do not like Cassandra Stress. I absolutely hate it. In fact, whenever I try to use it, my gut tells me this should be a lot easier, and it should be. I'm going to say that I'm 100% right on this one. So I built a tool called TLP Stress. TLP Stress also acquired by DataStax with TLP. Again, I forked it. I've added a whole bunch of useful stuff on top of it since then. So my version of TLP Stress is way ahead of the one that's over at DataStax right now. There's also NoSQL Bench. NoSQL Bench is the benchmarking tool that DataStax is putting their muscle behind. And that's maintained primarily by a guy named Jonathan Shook. And NoSQL Bench is kind of has a few major advantages over TLP Stress. One of the big ones is you can benchmark anything, and the other one is it's highly configurable. So TLP Stress is really meant to be like you take it out of the box, and it comes with workloads, and you might say I'm just going to run a time series test, or I'm going to run a key value test, and then through the use of the parameters that you pass it on the command line, you can kind of mold that workload to fit what you're looking for. And that works well for me. Some folks, they say, I want to benchmark my exact schema with this exact type of settings. Okay, that's not TLP Stress. Yeah, that's more of a NoSQL Bench. You can develop your own workloads for TLP Stress, but you have to write them in Kotlin because I don't feel like developing another configuration language. I just don't care. NDBench is the final one that I'm going to talk about. That was used heavily at Netflix. I'm actually not that familiar with it, oddly enough. Even though I was there for a year and a half, I never actually used NDBench. It just didn't. I didn't have a use for it. I want to do things my way, so here we are. TLP Stress. That's what I like to use. So I'll add the links for those into the description. So just go back to the beginning. We covered 3 things today. Super important when you're doing any sort of database optimization, or really any optimization at all, any sort of performance analysis. These are really useful. Have the right methodology. I talked about the OODA loop and the use method. Definitely check those out. Get familiar and make it a deliberate thing that you do. So we at TLP, we would actually write observe with our observations. Orient, this is how I see things. Decide, okay, now I know what's going to go on, and act. You do this, I do this, you do this. It's a really good process to get familiar with. I definitely didn't invent it. I didn't even bring it to TLP. I got this from Aaron Morton, another Cassandra committer, PMC. member. Great guy, former boss, friend. Um, Number two, observability, right? You got to have the right tools in place. That means your dashboards to help you figure out what's going on at a high level, your and then your tools in the actual system to be able to figure out what's going on, and then know how to interpret that information. And lastly, practice. I talked about TLP cluster. I talked about Axon Ops. Both are easy ways. DataStax offers Astra, another way you can kind of get in there. I'm a hands-on person, so I want to build SSH into everything, and I'm not quite as trusting with my data, so I want to own everything. So if you look at like, if you're gonna deploy everything yourself, and you want to figure out, how something's gonna work in your environment, it's a good idea to have tools that work in your environment. So Astra might not be the right fit, but if you're gonna go to Astra, use Astra for benchmarking. You want to be as close to production as possible. Okay, and then last, almost forgot about this. So if you enjoyed this, I am starting up training this year. So I'm currently working on my training program. It is, I believe we're going to do an 8-week program, 90 minutes a week. There's going to be homework. There's going to be class exercises. You're going to work with other people. You're going to meet other people. This is going to be a really, really great way. If you aren't super confident in your ability to run Cassandra, or even if you are super confident and you just want to get better, I'm going to be sharing a lot of useful stuff. Think this session, but for 8 weeks. And I'm going to be really kind of getting into like, this is how you need to run Cassandra if you want to run it at the highest level. So if your goals are to run database systems, if you want to run Cassandra at Apple or at Netflix or at CrowdStrike or any of these companies that require super, just a ton of information, like a high level of expertise, my goal is to help you become an expert. So let's see if we got any questions here. Oh, I love, hey Sarma, training from John will be amazing. Thanks, buddy. I appreciate that. I want stuff right away as well. Yeah, impatient. On-site training. Yes, so there will be two types. So the training will be, the one that I'm going to be running initially is going to be virtual. So you won't have to go anywhere. It'll be virtual training. We're just going to do it like this. I'm working on the exact details of it. So I'm not sure exactly how some of it's going to work, but it will be virtual. I will, however, also be offering on-site training. So if there are teams, like if you have a team now and you're running Cassandra and you're interested in, having me come in and work with you for 3 days and to help solve all of the stuff that you're like dealing with, we can definitely do that too. So this is my goal at this point. I've consulted with many teams, but my goal now is to help as many people as possible. I no vacation to guy. I mean, you could come out to Cali and do it remotely. That's okay. If my goal now is to just help as many people as possible, which is why I'm doing this, which is why I'm going to be posting lots of videos, which is why I'm going to be doing Q&A sessions and AMAs. I really, really want as many people to be successful because the better that we do as a community, the better the database will be, and really the better we can all be. I think if we can become a rock solid group of experts and build a bigger community, it'll be nothing but good for the project. There's no downside. So I'm really excited. You see John in your efforts. Oh, thank you very much. Let's see now. Problems within Cassandra or any databases, wouldn't the source most of the time potential be schema design? A lot of problems are schema design, yes. So, for example, if you've laid out your table and you do 10,000 queries to the database instead of querying a single partition, problem, right? If you don't lay out, if you don't take into account what might happen with unbounded partitions, like let's suppose you have time series data and you're logging, 500 events a day. It doesn't seem like it's going to be that much. But if you forget to put a TTL on them and you use size tiered compaction strategy, and all of a sudden your payload size changes, and then it goes to 10,000 requests a day, you can end up with like huge partitions, and huge partitions lead to all manner of problems with compaction, reading, read repair, regular repair. There's a really good blog post that my old coworker Mick from The Last Pickle wrote about large partitions, and recent versions of Cassandra have gotten a lot better about handling large partitions. I think maybe version 3.6 or 3.8 or something like that. 5.0 should be even better. I need to test this, but the new some of the new data file formatting stuff that I believe has gone in there should actually be great for larger partitions. But larger partitions are not good from those other. They're still not good for repair, right? We still have to do too much work in repair on large partitions, especially read repair. So that can be problematic. Tombstones can be a problem. With Cassandra, the thing that's weird is that the schema design is most people, I think, including myself to a degree, I think of schema design as the keys that are present and then the read patterns. But it's really important to actually also think about compaction. If you have, for example, a workload where you do a ton of deletes, if you're deleting arbitrary stuff like point deletes and large partitions, and you're using size tiered compaction strategy, you can end up with a lot of SS tables that your read path has to look through in order to send back results. So, compaction, compression, all of those table options I consider part of the schema, and they are pretty important. So, so that can be, schema is super, super important. There's a lot of things, unfortunately, that are super important. The tricky thing about schema is that if you don't get it right up front, then now you have to do a redesign and you have to do a data migration. And whenever you do a data migration, that becomes tricky because now you have to ensure that you have consistency across the different views of your data that you have. And you also have to build a migration system into your code base. So you would need to first do a deploy that changes your writes so that you write to both spots. And then you have to do a migration, and then you have to do another deploy that makes you read from the right location. And then you can finally drop the old table. And that was a lot of steps. Migrations can be really, really painful. Especially if you don't have the tooling already built. So if you then start, looking at Spark to do the migration, well, now you need to ask yourself, am I going to run, if you only have one DC, am I going to run Spark in my one DC? Now you have to set up another DC. Now you just doubled the cost of running your cluster. So there's all these kind of, there's a million rabbit holes that you kind of go down, and you're just oh my God, this migration was supposed to be this should have been simple, but I ended up having to deploy a Spark cluster. I had to double the size of my DC. 3 months later, you're finally ready to do this migration, if it's a big enough table. So yes, schema, huge problem if you do it wrong. You got to be really careful. That was a really, really long-winded answer, but I hope that was happy. I hope that was a good one. I hate retransmit, and I still don't quite get it and how to fix it. TCP retransmit is typically going to mean that you have issues with your network reliability. So this is one where you're going to actually probably need to work with a network team in order to figure out how to fix it. This is one thing that I would basically just be here's the information that I have. I do not know what you need to do with the hardware. I'm not really the person that goes in and figures out what's wrong with networking switches. It's just not me. Maybe one day. But for now, just write it up and I pass it to somebody else. Let's see now. What do we have here? Schema/data model. How about deleting many millions of rows of data taking 24 hours to delete? Could that be wrong designing or Cassandra configuration issue? Yeah, if you're going to delete hundreds of millions of rows, that can definitely be a problem. There are there's a few different things here that are that kind of come into play. Um, One, if you're deleting, let's say you have a partition with 100 rows. If you're deleting them, if you're issuing 100 deletes, that's going to be significantly worse than issuing a single delete across the entire partition. And if you've got 5 partitions that are sequential, you're better off doing a range delete than you are doing 5 individual deletes. So there's that. Deleting lots of data all at once is always tricky with Cassandra because now repair becomes even more important because you don't want to see data get resurrected. You want to make sure that you're not dropping mutations. If you have nodes that are dropping mutations, then you're at risk of, even though the hinted handoff is supposed to take care of everything, you are at risk from having data get resurrected. It's possible that you could like store a hint on a node, and then that node could die, right? You have 3 nodes, A, B, C. C goes down, right comes into A, writes a hint. A goes down, C comes back up. Hint's never delivered. A is replaced. Now C has data that's supposed to have been deleted. And if the tombstones are cleaned up on the new A and the new B, before C has a chance to get those tombstones replicated via the repair process, then you could end up having a resurrection there. So lots of problems associated with just issuing bulk deletes. It's not something I'm going to say like don't ever do it, because there's definitely valid use cases to do it. You just need to kind of understand what the trade-offs are, and I listed a handful of them. So gotcha. I hope to get the budget approved soon. Yeah. Noisy alarm. Yeah. Well, happy to help. I am, I mentioned training, but and my consulting a little bit, but I come in, I help out teams. I love to help people fix stuff. So this is, these problems are exactly what I've been working on for the last several years. And, training will cover some of this stuff. Consulting can cover some of this stuff. But more than happy to come in and help you folks out if you have questions. If you're curious and you just kind of want to have a chat, we can schedule a quick call. It's not a big deal. If I can solve your problem in half an hour, then I don't want your money. Like I'm not really interested in doing 5 hours of administrative work in order to get half an hour of cash. I'd rather just help you guys out. Hopefully, if you're watching this and you're interested in either training or consulting, definitely get in touch with me. Go to rustyrazorblade.com. I've got a mailing list also linked here in the description. I'm going to be sending out information about training, tips. Whenever I write my blog, like I'll be sending out like information about that. I'm really just trying to help as many people as I can. So even if we don't end up doing training, even if we don't end up doing consulting, hopefully you get some useful information out of the blog. But if you are interested in those other things, and you are interested in kind of some of these tips and the research that I do, subscribe, because that's going to be the easiest way. I said I wouldn't be one of those people that said like and subscribe this thing, but I'm pretty sure it will help. So I appreciate it. All right, I'm going to sign off now. If anyone needs to get in touch with me, please find my contact info in the description, rustyrazorblade.com. You can reach me, and or you can reach me on ASF Slack. If you're not on the ASF Slack yet, it's a really great place to get some help. I'm Rusty Razorblade on there. So yeah, get in touch, and good luck. And if this helps you, please let me know. Alrighty.